be focusing mainly on like the basic theory, and then we might have future sessions which involve like hands-on, like coding as well. So there's a small disclaimer. We are also students, the speakers, so we'll try our best to answer the questions like when you ask them, but if in case we can't, we'll obviously get back to you. So yeah, so these are the topics that will be covered today. So in unit 1, I'll be covering logistic regression in brief, and then basically very fundamental concepts like what is neuron and about neural networks, activation functions, and forward propagation. And at the end of unit 1, I'll provide a link to a TensorFlow playground where you'll be able to apply what you learn and then just explore the neural networks there. So yeah, and then in unit 2, Manish should be talking about how to train neural networks and about backpropagation. So basically these are the topics that we'll be covering. And so yeah, so let's start with unit 1. Okay, cool. So basically logistic regression. I won't go into much depth here because this was one of the prerequisites. But anyway, the basic of logistic regression is used when the target variable is categorical. What I mean by this is when you have to classify the target variable. Like here you see you are giving a bunch of inputs and then there is a processing sort of thing, and then you get either happy or sad. So for example, you use this when to predict if a mail is spam or not, or when a cancer tumor is malignant or benign. So what happens here is the data is fit into a linear regression model, and then it is acted by a function, by a logistic function, which predicts whether it's 0 or 1 or happy or sad, and then basically the value ranges from 0 and 1, the output. So this is basically logistic regression. I'm not going into depth here, but yeah, it was used in the 20th century, like for social purposes, social science purposes basically, and then it has since then been used for machine learning applications. So yeah, here's a small introductory video before we actually start going into neural networks. So just watch this.
Hi, I'm Nat. I'm Love, and this is our 20% project where we go.
So one thing is the audio. Is it audible?
Yes, it is audible. Just continue. Let's see.
Okay, sure.
Out about different Google stuff we're curious about. Last year, we got to make a documentary about how voice search works. And that was the first time we heard about something called machine learning. Since then, we've been kind of fascinated by it. So today, we're talking with Greg and Chris to learn more about it. How would you describe machine learning to someone?
Well, there's a lot of problems that's really easy to solve with computers. Computers can go and simulate how galaxies move and how the courses of asteroids going and how close they're going to come to Earth. I could never hope to go and do that, but I can go and do this problem, like recognizing that that's a tree, which is so much tremendously more difficult for a computer.
It doesn't feel like intelligence to us because it's so effortless as a human being to do it, but for a computer, it's actually really hard.
Because the real world is kind of messy and unpredictable at times. The strict logical rules that go into traditional programming just don't work.
Instead of going and writing programs that solve the problem, we write programs that learn to solve the problem from examples.
And it's this process of learning that allows them to improve over time and to actually be more clever than they would be if we wrote down a very rigid set of instructions for them to follow.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation, email spam filters. When you go to the ATM and you give a check and it can read the handwriting. or a Photos app that can automatically organize your photos based on the things that you like to take photos of. Like, here are all my mountain photos, here are all my food photos, here are all my dog photos, here are all my feet photos.
Everything from facial recognition to going and trying to recognize whether a particle is present in that particular collision at the LHC.
Which we just like to take a time out to say is that big tube in the ground over in Europe that smashes particles together at really fast speeds so that scientists can use that information to unlock the mysteries of the universe, among other cool things. Now back to our episode, because I am getting really dizzy doing this.
So researchers and scientists are still experimenting and trying to find the best ways to teach computers how to learn. But a lot of the progress is coming from these algorithms that are based roughly on how the human brain works, and these are called artificial neural networks.
So an artificial neural network is something that it's a rough mathematical cartoon of how a biological neural network works. In a biological brain, we have individual cells called neurons. Each neuron looks at what its neighbors has to say and then decide what it wants to say. And in artificial neural networks, we have little mathematical functions. We put them in some organized structure, and then we say, okay, you guys all together, learn to do this task.
We have lots of neural nets that are really great at going and recognizing, this is a cat, this is a dog, this is a frog, this is a mouse, this is a horse, this is a truck, and things like that.
So take, for example, trying to recognize what this is.
So it used to be that we were really proud if we could get a neural net with 3 layers to work. And it's recently that we've made a lot of progress on techniques that allow us to train much deeper neural nets.
And that's why this kind of machine learning is also called deep learning. A neuron in the bottom layer is just going to be looking at a tiny piece of the picture and making some computations about it. It doesn't understand anything about dogs specifically.
But what the neuron does understand is it says, I'm giving a signal. It's useful for somebody who's giving a signal, who's giving a signal, who's giving a signal, who's giving a signal.
They're kind of able to unfurl this really high-dimensional knot and pull it apart and make it easier to go and separate different things that are close together on the surface from things that were tangled all together earlier.
But then at the top, we'll have 2 neurons, and these neurons look at the whole picture so far.
They're basically experts at making the final call, figuring out, all the layers below me said these things, so I know that this is a dog, or at least I'm 92.4% sure that it's a dog, so it's basically a dog.
And while there's been a whole lot of progress with teaching computers to learn, they're still much slower learners than we are, and they make mistakes that you and I wouldn't.
So what I was working on is sort of trying to find a way to go and look at a neural net and ask, what does the neural net think the platonic ideal of a cat is, or the platonic ideal of a dog, or anything you can classify as? And suddenly you can go and ask, neural net, what do you think cat looks like? You get a picture of a cat. Or, neural net, what do you think a barbell looks like? So these weights. And it goes and it shows you a picture not only of a barbell, but of an arm attached to a barbell. So the model thought that the arms, it had only learned what barbells were from looking at pictures of barbells. They're often held by muscular weightlifters. And so it learned that there was, barbells have arms attached to them.
It takes them a long time to learn. You show it a picture of a school bus when it's early in learning. The very next time you show it a picture of a school bus, it's only a little bit more likely to say school bus. It doesn't get it, even though that was the very last thing it saw. Whereas, say to a kid, that's a filing cabinet. And then a second later you say, what's that? He's not going to be like, shoot, right?
Well, the more you describe this, the more I'm amazed by human beings.
Yeah.
The effect is wow, human beings are really amazing.
We're really amazing learning machines. Oh.
Okay. So basically, this is the link to the video.
Paste this in the chat box if it's possible.
Yes. I'll put these at the end if that's
Okay, that's fine. That's fine.
Yeah. So, a neural network. So, what is a neural network? So, in short, if we think about it, it's just a mathematical function. So, it's basically like you have an input, and then this neural network maps it to the desired output. So, it's just a mathematical function which maps a given input to the desired output. So basically what it does is, it's like a computing technique which is like similar to how brains compute things, like how a brain works, like as a connection of neurons, as a neural network. It's the similar way, using artificial neurons. So in this picture you can see there's a cat image input, and then like the processing happens, and then you get the output as the cat. So basically what is happening is there are different layers. So each plane here, as you can see, is called a layer, and the different layers are computing different things. And then at the end we see that like based on information given, it decides that it's a cat. So this is a very high level view of a neural network. We'll be going into depth soon. But this is basically what happens. You are giving an input. It, works as if, it's like similar to how a brain works basically. And then it gives an output. So, yeah. And then, these dots you see on each plane are neurons, or you can call them neurons or nodes. So, yeah, we'll be seeing more about neurons too soon. Yeah, so neuron versus neuron. So basically the first picture is a biological neuron, and the second one is an artificial neuron. So, so you can see the similarities here. The inputs are like, the dendrites basically, but then you're getting an input and then it's computing something and then it's giving an output. So you can see the similarities in both the things. So there are a few things here, like in the artificial neuron, which might not make sense, but let's see. So there are W0, W1, W2, which are called the weights. Okay, so these are like the weights, weight connectors, and then X1, X2, and X0 are the inputs. Okay, so there are inputs and then there are weights, and then what a neuron does is, it takes the weighted sum. Okay, it takes the weighted sum and then adds the bias. Bias is basically a random number b here, and then it adds that, and then there's this thing called activation function. So we'll come to know what it is later on, but then so we'll take the f of the weighted sum and then output that basically. So this is a short explanation of what a neuron does. We'll look into it in more detail. So this is like, you can see the similarities here between a biological neuron and an artificial neuron. So yeah.
Poornima, so
Yeah.
is it that the X0s, X1 and X2 are those outputs of other neuron?
Yeah, it
like
could
in
be.
biological
It could
neurons?
be. Yes, it could be. It could be the output of other neuron, or it could be like the first input of the, it could be our input too. Of course, in a neural network, these X0, X1 could be the outputs of other neurons. Or if this neuron, which in particular, if it is the first neuron, then those could be the inputs which we give.
Okay, right. Okay.
Okay, yeah. Cool. So moving on. So what exactly a neural network, does is basically, you're given an input and then it does some computation, and then there is an activation function. It's basically like, an if statement. Then, if it is yes, it activates the neuron. If it is no, it does not activate the neuron. It's something like in brain also that happens, like activation of neurons. So it's like, in a similar way. You can see some examples. So if we give an input as 5 and the condition is less than 10, then it activates the neuron. And similarly, here 7 does not have a curve, so it does not activate the neuron. So
What does activation means actually? Is it like that the neuron, if it is activated, it will like pass on
yeah,
the output?
yes,
Or
yes. So yeah, activation basically means that if it's active, then it's like taking part in the a decision making process, or it's like it affects the output basically if it is active. So if it is not active, then its output doesn't matter much in the face of the the whole neural network's output, if that makes sense. Yeah, okay, cool. So these are the examples. So basically what happens inside a neuron. So we have seen what a neuron is. Neuron is basically like a node in a neural network, right? So what exactly a neuron does. So this is basically like the block diagram of a neuron. So there are like basic, three basic elements which can be seen. So the first thing are synapses. Okay, synapses are connecting links, and then they have you can see here synaptic weights. So they have weights. Okay, so they have a strength, or a weight is basically how much you're allowing that input to affect the output. Okay, so it's basically like you're taking the weighted average, in the sense your w you can see the weights, right? So it's basically like how much you're allowing that particular input to be to affect the output. That is like depending on the weights, you're deciding that. Okay, so you have an adder here. It's for summing the weighted outputs. And then there is a bias. Bias is again a constant value. As I said before, then the output, which is got from the adder, is then put into an activation function. The activation function produces the final output of the neuron. So basically what a neuron does is it takes these inputs x1, x2, okay, and then it does all these computations, and then it gives the output. So this is basically like the block diagram of what a neuron does. Okay, so we can see a little math here. It's the same thing, but a little mathematical. So here phi is the activation function. Okay, so we as you can see, we're taking the phi of the weighted average. So what a neuron does, as I said, inputs, okay, weights are there, inputs are there, then you're taking weighted average, basically x1 w1 plus x2 w2, something like that, and then we're adding the bias, and we're putting the activation function on the output of the adder. So activation function on the sum. So so you can see here activation function on the sum here. Okay, if this is making sense. So x1, as I said, xi are the inputs, w are the weights, b is the bias, and phi is the activation function. So the output is the activation function, which is acted upon the weighted average plus the bias. Okay, so this is the same thing, basically like an extension. What we can do is, instead of adding the bias separately, we can take bias also as the input of the input, because it's the same thing, right? Anyway, we're going to add them. So here, so we're considering the bias as input. So as we are adding x1 w1, so here we can put the bias as w0. Okay, so we have x0 as 1. We're basically adding another input. Instead of adding bias directly, we're just adding bias as an input. So we are putting x0 as 1 and then putting w0 as the bias which we need. So x0 into w0 will again be bias that will be added directly. So it's basically the same thing. It's just a little representation change.
Poornima, one small query.
Yeah.
What is the significance of bias?
Yeah. So basically, bias, I think, is mostly like, it changes the output in a constant way. Like, when we are changing the inputs, the bias won't get affected, right? So it's something like an offset sort of thing. So it depends again, like, every neuron will have different biases and stuff, but something like an offset. Okay, so like if we need something like for the activation function to work properly, if we need a certain offset, I mean, see, if when we see the activation functions, I think you'll understand, because uh, we should get an output from 0 to 1, right? So the input should be according to that. So the bias would help regulate the overall sum.
Okay, so basically for activation function to work properly, maybe sometimes we need
Yeah,
an offset
yeah,
to the
yeah.
output given by the summing junction.
Yes.
So, okay, I got it.
Manish, you want to add anything here? Okay, fine. Let's continue. So, is this fine? I mean, does this make sense? We didn't see why this is happening yet. I'm just telling what is happening. So, is this making sense?
Maybe the attendees can put up in the Q&A section
Okay. Yeah.
if they have any
Yeah.
doubts
Okay.
till now.
Yeah. Okay.
Hello.
Yeah.
Yeah, I had some problem. Okay. Asha
Okay.
was asking about the bias, right?
Yeah. Yeah. Yeah.
So the bias is something like suppose you have you want to suppose you want to find some boundary that is not passing through the origin. Suppose all your inputs are 0, but you want to have some output that can that is actually that you want to have an option that can push the boundary away from the origin, so that the bias helps in that. The boundary here in the sense is a boundary that I'm going to draw between my classes of data.
Okay, so basically, if all of my inputs are 0, we still have to show some decision.
Yes,
But
we have to
if we
still show
don't
some
have,
decision.
but if we don't have a bias, our neuron will act like nothing has happened, like it's 0.
Yes, exactly. Actually, it's a little bit more than that. A bias is something which helps you to. But if you don't have a bias in your model, it constrains your model to making decisions that always have the boundary passing through the origin. So basically, it tells you that. So suppose your classes are far away from the origin. Some hypothetically speaking, let's say I am having an origin and then my classes are far away from the origin. But in case if I don't include the bias, my decision boundary will be constrained to pass through the origin. That is not something which we don't want.
Yeah, because our classes are always, say, far away. Maybe
Far
in
away.
some cases it is far away.
Yeah.
Then it's of no point to make the class boundary to go through origin.
Yes, exactly. So we want to have freedom to move the boundary away from the origin. So that the bias helps in that.
All right, it's more clear now. Yeah.
Okay. So moving on. So basically, this is what a neuron does. So you have inputs, you have the weights, you're multiplying, then adding the bias, then putting the activation function and giving the output. Okay, so let's move on. So you have seen what neurons are, or basically what neuron does. So now what are neural networks? So as you know, neural networks are basically a network of neurons, but so how they compute what we want, or how they process the input is what we can see here. So basically these circles are neurons or nodes, and then the middle layers are called the hidden layers, whereas there is an input layer and an output layer. So basically this is like a simple neural network. So I can like give you an example. So you can imagine like an assembly line in a factory. Okay, so in this assembly line, one worker receives an item, then makes some adjustments, and then passes it on to the next worker in the line, who who again, does the same, like who again makes some adjustment and passes it. So this process continues until the last worker in the line, like finishes it and then like takes it out or like sends it out of the factory. So in this analogy, there are like multiple layers to the assembly line. And the products like, move between the layers, like as if they move from worker to worker. I hope you're getting this. It's basically like an analogy which is like explaining the working of the neural network. So the assembly line also has like an entry point, exit point, and similarly neural networks are like that. So it can be thought of like a simple production line made of like input layer, hidden layers, output layer. And the input layer here is basically where the data is fed into the network, so basically where the inputs are given. And the hidden layers you can think of as like the workers handling the data, like as in a factory the workers are handling the data, and before they pass it to the output layer or like the outside world. Yeah, of course, in the instance of a neural network, the workers are called neurons or nodes, and they manipulate the data through like a series of mathematical functions, as we have just seen. So basically each neuron does what we have seen till now with different weights, different biases, like with different parameters of their own. Each neuron does that. So and then we're having a network of neurons. So basically the input for the hidden layer comes from the input layer. Input from the hidden layer 2, input for the hidden layer 2 would come from the output of the hidden layer 1. Okay, so this is basically like a simple neural network, how they work, how it works. So yeah, so one more thing we can think of is like it might not be exactly accurate, but we can think of it like a particular layer learns some features. Suppose we are passing an image. Okay, so computers can't understand images, right? Like they don't know, they just know pixels. So a neural network, what it does is it can build a simple representation of the image. So in the early layers, it maybe identifies like the simple things like corners or edges, and then in the later layers it can learn complex features like eyes, nose, and then basically in the output layer it's like putting the whole thing together and then identifying. I mean, of course, computer doesn't know what a cat is or what a dog is. It's basically like learning learning through the neural network. It's coming to a decision that it's this much percent sure that it's a cat or a dog. So basically this is what a neural network does. It's like I mean you're giving an input and then it's processing. As we have seen, like each neuron does the same work, and then it's giving the output. So how it does exactly, like we'll come to that like in unit 2 also, because we have still not understood how exactly it's arriving to an accurate solution. Okay, so that would be discussed in unit 2. So basically, this is like the simple example of a simple neural network architecture. There are, of course, different types of neural networks, which would be like arranged in different ways, or the layers would be different. Yeah. So this is again an example of identifying the the species. Okay, so these are like the common activation functions. So what this says is it's basically like if we want the output to be between 0 and 1, then the sigmoid function, the sigmoid activation function is defined as shown, and then that converts the input to an output between 0 and 1. Something like taking the input and then, giving out the probability of it being true or something like that. So there are, of course, different types of activation functions. There is ReLU, rectified linear unit. So it was discovered after the sigmoid function, and it works a little better often. And then it's, of course, like easier to compute. So it's defined as max of 0, x. There are other things like TANH, leaky ReLU, which are used in different scenarios. So which activation function to use depends on what you're doing, and various other factors. So like little research on that would be you can like check it out, like which activation function is used. So this is basically about the activation functions. These two are like very commonly used. So yeah, forward propagation. So what is forward propagation? So it's nothing except propagating the data through the layers, from the input layer through the hidden layers and then the output layer. It's basically propagating the data forward in the forward direction. Okay, so we have just seen the calculations before. I mean, it's the same thing. It's basically how the data is propagating through the neural network. Like you have the inputs, then it's giving the output to the hidden layer, and then the hidden layer is again computing, and then so on. Like it's moving in the forward direction, right? So that is basically forward propagation. I have one more small video here, which you can just see on forward propagation.
We'll start by showing how neural network models use data to make predictions. This is called the forward propagation algorithm. Let's revisit our example predicting how many transactions a user will make at our bank. For simplicity, we'll make predictions based on only the number of children and the number of existing accounts. This graph shows a customer with 2 children and 3 accounts. The forward propagation algorithm will pass this information through the network to make a prediction in the output layer. Lines connect the inputs to the hidden layer. Each line has a weight indicating how strongly that input affects the hidden node that the line ends at. These are the first set of weights. We have one weight from the top input into the top node of the hidden layer, and one weight from the bottom input to the top node of the hidden layer. These weights are the parameters we train or change when we fit our neural network model to the data. So these weights will be a focus throughout this course. To make predictions for the top node of the hidden layer, we take the value of each node in the input layer, multiply it by the weight that ends at that node, and then sum up all those values. In this case, we get 2 times 1 plus 3 times 1, which is 5. Now we do the same to fill in the value of this node on the bottom. That is 2 times minus 1 plus 3 times 1. That's 1. Finally, we repeat this process for the next layer, which is the output layer. That is 5 times 2 plus 1 times minus 1. That gives an output or prediction of 9. So we predicted 9 transactions. That's forward propagation. We move from the inputs on the left to the hidden layer in the middle, and then from the hidden layers to the output on the right. We always use that same multiply and then add process. If you're familiar with vector algebra or linear algebra, that operation is a dot product. If you don't know about dot products, that's fine too. This was forward propagation for a single data point. In general, we do forward propagation for one data point at a time. That value in the last layer is the model's prediction for that data point.
Okay, I hope that made it a little clear. So basically this is the link. I'll just put the link in the chat later. Yeah, again, it's basically forward propagation. So basically this red box is a neuron, and similarly there are 4 neurons here, and then each one is taking the input and then taking in the bias, adding it, and then putting it through the activation function. Okay, so basically this is again forward propagation. Yeah, so here's a small animation which shows forward propagation. It might look complicated now, but like I can like share the slides if possible. Like you can check it out later. This is again basically forward propagation only. It's nothing but just what we have discussed so far, like how a neuron does the calculation. Every neuron is doing the same sort of calculation and passing it on to the output layer. Okay, cool. So yeah, I would request everyone to go to this link. I'll put it in the chat box right now. And what we can do here is, this is basically a place where you can design your own neural networks and then see how it works out for like different inputs they gave. If you like when you go, you'll understand there. It's basically you can select the number of neurons, you can select the number of layers, you can select what inputs to give. So yeah, I'll put the link
Poornima,
soon.
can you show
Yeah,
a demonstration of how, or are,
yeah, sure.
yeah,
Sure. It's basically like they can explore on their own, but I'll just show it. Yeah. Uh, yeah. So basically, these are the videos used. I'll again put the links, and again there are sources. So yeah, this is the end of Unit 1. Thanks, and I'll just put the link and give you a short demo, and then you can like explore for some time on your own, and then after like a little break and a Q&A session, we can move on to Unit 2. Okay. Fine. Okay. I hope everyone went to this link. Can you see my screen?
visible?
Yeah. Okay. So basically, this is like this sort of like where you can just play around with the neural networks. So suppose you want more neurons or uh, different sort of data sets, and there are different activation functions which can be used, and then you can see the output here, how it's like classifying or I would like everyone to open it on their own. So yeah, suppose we're using this. Okay, so here if you want to separate these two, like orange dots and blue dots, we can't do it with a straight line, right? We would need a non-linear boundary, like we would need a non-linear decision boundary. So if we use just x1 and x2, like here, as you can see, x1 is like dividing it vertically and x2 is dividing it horizontally. So if we only use x1 and x2, we'll see what happens. We can just click the play button here and see. So it's basically it's becoming like a triangle here. Like see, in the hidden layers, uh, you know you can see the shape which is trying to detect, like in each neuron. So if we subtract the number of neurons, if we decrease, so we are not having a proper boundary here, because like we are not having enough number of neurons to detect the required shape. Suppose we take something else, x1 square, x2 square, it becomes like almost a circle. like basically it's nothing like you can just play around with it and explore it on your own. You'll have different learning rates, and yeah, so you can see like the loss and all that. You can of course add more layers too. uh, you have different data sets here, then you can see the noise. I mean, change it. So yeah, I would like like everyone to just play around with it for some time, see if you're getting what it is. So yeah, I'll just stop my screen sharing.
Okay. Yeah.
Yeah, okay. So maybe we can give them like 10 minutes or something just to just play around with it, and then we can in the
Maybe we
meantime
will
just
mail
give.
all the links together again. So I think we can continue with Manish, his part.
Okay, okay, fine, cool. So should I put the links here, or
We will
will
mail them.
like will
We
you
will
mail
mail the
them?
slides also if
Okay,
possible.
okay, cool. Okay, so then Manish, fine. Let's on to unit 2. I think we're having a question here. Um, is it like different hidden layers of a neural network learn on different features of input? And yeah, it's something like that. There's a question in the chat box everyone can see. So basically, different layers learn different features, and then they give a single output. It's something like that. Yeah. Okay. So I guess Manish can continue.
It's more like different units in a hidden layer can learn different features.
Yeah. Okay. Isn't that?
If
Yeah.
I hope Siddharthani's Nayak's question is answered. Let us know if it's not.
I don't think they can
You can just text there if it's answered or not.
Basically, is it that different parts of neural network, they are responsible for detecting certain features in the data?
Basically, every unit in a hidden layer is responsible for detecting any one feature in the data. So, so actually, there is a bound on there is some kind of a constraint on how many hidden units you can add in a hidden layer. So that is the reason why you need to have more hidden layers.
All right. I think we have another question.
Does more hidden
So
layers
Siddharthini has,
accuracy?
yeah.
Yeah, so it's not necessary that more hidden layers means more accuracy. It can be the other way around also. More hidden layers can actually spoil the stuff, spoil your work. More hidden layers actually, gives you more parameters, more weights that the hidden layer, that the neural network has to train, and this will kind of cause the model to overfit. Okay, so when I say overfit, the thing is that the model actually by hearts everything that all the data that is given to it. We don't want that to happen. We want the model to generalize.
So Manish, basically, what does overfitting means is if it byhearts the data that is fed into, so our model will not be able to detect would not be able to judge new inputs, right?
Not also, but the thing is, it does not perform as expected on new inputs. That is the point. It has by-hearted a set of data, and then it is saying that I will only go by these rules that I have learned. I am not flexible anymore to learn anything new.
That answers. Yeah.
Any more questions? You can feel free to ask here. Are you guys aware of this concept of overfitting and underfitting? If anyone knows about these things.
Guys, you can just put yes or no in the chat box if that's okay.
Okay, so I'll just tell you about the concept of overfitting and underfitting. The idea is that when you want a learning model to learn, okay, a neural network is, for all technical purposes, it is called as a machine learning model. Okay, there are many other machine learning models, and we have only chosen to cover one particular model called the neural network. So in a in any machine learning model, the idea is that we don't want the machine learning model to by heart the data that is given to it. So if it sits and by hearts the data, then it's called overfitting. That means that we will not get the desired output when new data is presented in front of it. It'll do a terrible job if new data is presented towards it, in front of it. So this concept is called overfitting. And underfitting is when it fails to learn on the training data itself. I hope this idea of overfitting and underfitting is now a bit clear. Poornima, do you have anything to add on to it?
Nothing much. Basically, overfitting is when it learns too much, and underfitting is when it doesn't learn enough. So basically, both are not desired. Yeah.
I don't know if the attendees are clear or not. So basically, machine learning models, basically there is a training phase and there is a prediction phase, right? For a subset of the machine learning models, right? So
Yes.
the thing that overfitting and underfitting we are discussing is the training phase, when we give some data to tell what is what and what is not. So from that the model is learning, and if it underfits, that means it is not learning enough, so it won't be able to answer some questions that we pose on by passing new data. And by overfitting, it means that the it is learning too much from the given data set only, so it won't be flexible enough to answer some questions on the new data. So am I right in saying that?
Yeah.
Okay, I guess then if there are no other questions from the attendees, we can move on to the unit 2. Manish, if that's okay.
I
We
think
have
he
a
has.
question.
Okay. Okay. When the model is training, is it that it starts at some values for weights? And yeah, it's something like that. So how it is training would be covered in unit 2 exactly, but it's something like it takes in the data and then gets a feedback and then adjusts the weights and biases accordingly, so as to increase its accuracy. It's something like that. Exactly how the training occurs would be discussed soon, like in unit 2. But it's something like what the question says only. Not exactly like as it gets more data, but of course more data would increase the like increase its accuracy, as long as we maintain the proper architecture. But something like it generates an output, gets a feedback, and then adjusts accordingly the weights and biases, and again starts to uh, generate an output. Exactly how it happens, Manish should be discussing in unit 2.
I guess we can start, Manish.
Yes, 1 minute. I'm just setting up. Hello? Yeah, okay. I'm sharing my screen.
Already.
Can you see my screen?
Yes.
Okay. Okay, so I'll be talking about how to train neural networks here. So what we have just learned is that a neural network is just a function. So it just takes some input and then it predicts some output. But the question is, why are they so powerful? Why can we use them to do any kind of prediction that we want? That's because they have a lot of parameters. These parameters are the weights. So the weights and the biases, these are things which can be tuned according to our interests, and we can help. We can help the when we tune it according to our interests, we can help the model to make decisions as per our requirements. So how do we tune it? So that is the question here. So this tuning is done using some we have something called as a loss function towards the end of the neural network. So we try to minimize this loss function so that the model can be tuned. Hello.
Continue.
Okay, so this is what we aim to do. We want to minimize the loss function. So how do we minimize the loss function? So the loss function is basically it is a function of the parameters of the neural network. So the neural network takes in some input and then it does some operation on it and then it gives some output. So we have some expected output. We give that expected output to the loss function along with what is the output given by the neural network, and the loss function calculates some loss. So in this whole process, what are the parameters, or what is the tunable part of it are these parameters, the weights and the biases of the neural network. So it's exactly these things that we aim to tune so that we can achieve the required performance. So loss function is a function of the parameters, and we aim to minimize the loss function. So basically our aim is to solve this equation, that is the derivative of the loss function with respect to the parameters must be equal to 0, and we aim to get the parameter values at these critical points basically. But how do we solve this equation? That is a question we have to ask ourselves. Analytically, it is not possible to solve. Neural networks can have like millions of parameters. Some of them, like the top-notch neural networks, have like around billions and trillions of parameters, and it is not possible for us to take a paper and pen and sit and solve and get the equations and then put it and then substitute to find how to tune the model. So analytically, it is not possible for us to calculate the loss function, calculate the derivatives, and then we set it equal to 0, and then to get the value of the parameters at those points. Now the question is, how do we do it algorithmically? So we want to minimize this thing algorithmically. So how do we do that? So we use a gradient descent. So it is a very popular algorithm. So the idea is that we have some sort of a surface in the particular space that we want to, from where, and then we have a starting point from where we want to go down into some valley and then go to reach the minimum. So the idea of gradient descent is based on the property that the gradient tells us the direction of the steepest ascent. So what we do is we go in the opposite direction. So if the gradient tells us the direction of steepest ascent, we go in the opposite direction, which is the direction of steepest descent. So we go in that opposite direction and we update the parameters as per this rule. So the idea is we start with some position on the loss function, and then this is the original position, and this is the gradient of the loss function, But then, and then we calculate the grade, and then we update the next step.
Hello, Manish. I think you're not audible. I think there's a technical problem. Manish will join again.
Hello, am I audible now? Okay. There is some problem by which I am being locked out. Okay. Is my screen visible? Okay. Okay. So I hope the part of gradient descent was covered. So now, so the question is, how do we calculate the gradients? So so gradient descent needs gradients, and we need to calculate the gradient. So gradient is basically the derivative part. So how do we, calculate the derivative of the loss function with respect to the parameters? So for that, we have a handy tool from mathematics called the multivariate chain rule. So if I have something like this, where I have a parameter t, and then I have two functions x of t and y of t, and then I have another function f, which is a function of these two x and y. So the derivative of f with respect to t is given by a nice formula like this. So basically what we do is we differentiate f with respect to x, and then differentiate x with respect to t, and then plus we add the other part, differentiating f with respect to y, and then y with respect to t. So this formula, I'm sure you guys will be aware of. It would have been covered in mathematics 1. So the thing is, this formula is little bit hard to come across like the moment you scale up the model. So I had another layer here. So you can visualize this thing as layers here. So I have this is a one layer setup neural network. So I have another layer here. The moment I add another layer, the derivative becomes more longer. So df by dt becomes more longer here. So I have to go here, and I have to apply the same logic, the first logic here again. So the thing is, things get complicated very quickly, and if you have multiple layers, then these derivatives will become very hard to calculate. So right now, if we have to sit and analytically calculate these gradients, it becomes very hard to do so. So how do we do it much more optimally? So the answer to this lies in another way of visualizing the same model. So we kind of visualize it in a more structured manner using something known as a computational graph. So a computational graph is basically a more structured and a more sensible way of looking at a model. So basically, I have a parameter t, and then I use it to find x of t and y of t, and then I use x and y to form f of xy. So I use a similar logic here. I have a parameter t, and then I find u of t and v of t, and then I use u and v to find x, and then I use u and v to find y, and then I use x and y to find f. So this kind of a structure and this kind of a order. So this provides an ordering to our calculation. So this is known as a computational graph. Now, computational graphs are very handy for us to calculate gradients. So suppose I have a computational graph like this. The gradient can be found out by finding all possible paths from the output node to the input node and multiplying the gradients around the individual edges. So this is one path like this, and I have another path like this. So so the path from output to input node, I have an edge like this, and the edge weight can be considered something to be as the derivative of the output node with respect to the input node, like this. So this gives you something like dou f by dou x, and then I have dou x by dou t, and then dou f by dou y, and then dou y by dou t. So this is another path here. So what we can do is we identify all the paths from the output function to the input parameter, and then we multiply the edge weights on the path, and then we add all the paths basically. So this is how we calculate gradients. So this is basically, so this term over here is basically the multiplication of all the gradients along.
Manish, you're inaudible.
Hello, am I audible now?
Yeah.
Okay. Okay, is my screen visible, right? Okay, so the idea is this. So we find out all the paths from the output function to the parameter that we want to calculate the gradient with respect to, and we multiply the edge weights along each path, and then we add up the multiplication terms for corresponding to each path, like this. So that gives us the gradient with respect to a parameter. Now this is a little bit more complicated example of doing the same thing. So we want to find the gradient of f with respect to parameter t. So what we do is we find out all the paths. So we have path 1 like this. We have, so the corresponding term for this path will be dou f by dou x into dou x by dou u into dou u by dou t. And then we find out something like this, the second path, and then we find out the third path, and then we find out the fourth path, like this. So so we have 4 terms here, and the gradient of f with respect to t is the sum of all these 4 terms. So this is the whole idea behind finding gradients with respect to some of the output function with respect to any parameter in a computational graph. So the short summary of how do we calculate gradients: we list all paths from the graph output to the parameter, and then we calculate the gradient along each path by taking output of individual partial derivatives between 2 consecutive nodes in the path. So what we have to do is, so the idea is still the same. So we find out all the derivatives along each path, and then we multiply them. We have to ensure that it's the derivative on each path is the output function's derivative with respect to the input node's derivative, and then we add the gradients of each path together. So this method of calculating gradients is known as back propagation, and it's also known as a reverse mode automatic differentiation. And this idea has been there for a very long time, but it was reinvented and in the context of neural networks in the, I think, 1980s by Hinton. And so his idea was that we can use this concept to train the data to generate the partial derivatives of of an output function with respect to any parameter. So let us try to apply this to an actual neural network now. So as we saw in the unit 1, we have the computational graph of a single neural network here. So we have some inputs and we do a multiplication operation here with respect with the weights. W0, W1 and are the weights, P is the bias here. And then we sum it all up. And then we pass it to an activation function. This is the activation function, and then we get an output. So this is a single neurons, the graph basically, how it computes the output. So when we do a forward propagation, this is what we do. So we calculate W0 into X, W1 into Y, and then we get something, get an output for the summation part. And then we do an activation here, and then we get a loss function here. So loss function is a function of the output given by the neuron and the true value here. And it's up to us to design how we want to calculate the loss function. Most commonly, it is something like a difference square or some more complicated loss functions, which for decision problems. But you can assume it's something like a difference square kind of an loss function. So this is what is known as forward propagation. So we get a loss output here. Now the thing is, we want, so initially these weights were given random values, and we got some random output here. Now we want to minimize this loss function. So idea is we want to propagate the error back towards all these weights to update them. So how do we do that? So we use the same principle of back propagation here.
Not audible, Manish.
Hello.
Yeah.
Okay. I'm sorry, like there's some bug, I guess. I'm not sure why this is happening. Is my screen visible now?
Yeah.
Okay. So what we do is to get the gradients of each of these weights. What we do is we kind of find all the paths from the loss function node, the output node, to these weights. So if you want to calculate the gradient of the loss function with respect to the bias, it will be just a multiplication of all these factors here. This is a multiplication of all these factors here. And then if I want to calculate the gradient of the loss function with respect to the weights, so it will be a multiplication of all these functions, all these terms here. Similarly for W1, it will be a multiplication of all these terms here. So, some of these terms are actually fixed. If I can evaluate them, so this term over here is actually it's just one, because I am differentiating the output of this of summation with respect to one of the terms, which is just one. And then similarly, this term over here is just equal to y, because the output over here was w1 into y, and if I differentiate this with respect to w1, that will be equal to just y. So that's why this term is y. So some of these terms are fixed, but other terms are not fixed. So stuff like these things are not fixed, because so the activation function is up to our choice. So in unit 1, we just covered about different kinds of activation function. There is a nonlinear sigmoid activation function. There is a ReLU activation function. So these things depend on our choice here. So since activation function depends on our choice, so these two terms cannot be calculated immediately, and there's no fixed formula to calculate them. So this is the idea of backpropagation. So what we do is to find out the gradient of the loss function with respect to any of these weights, we just find out the product of the individual derivatives on a path that connects from the loss function to the corresponding parameter. So this idea is so there's one more thing here. We also need to calculate the we also need to calculate the derivative of the loss function with respect to the inputs sometimes, or actually in most of the times, because in case we have another neuron connected over here, so in case we have another hidden layer coming over here, so we need to propagate this gradient to that layer also. So that can happen only through these inputs to a particular neuron. So a path has to be formed like this, and it has to go backwards here. So some details about how to implement this thing. If you are aware of graph algorithms like depth first search, we can list out all the paths from a particular from a particular node to any other node using this concept of depth first search. But alternatively, we can also use a greedy algorithm approach. So a greedy algorithm approach, what we basically do is we nicely put all these things and we pack all these gradients in a nice matrix. And then we use the properties of matrix multiplications to do all these calculations for us. So that is one way of doing it. And then why it's a greedy approach is because we need to calculate some stuff to the previous layer before we calculate something for the next layer. So the gradients of the previous hidden layer has to be calculated before it is calculated for the next layer. So this is why it is also known as a greedy algorithm approach. And such methods are used in libraries like TensorFlow and PyTorch. So if in TensorFlow there's a provision where you can actually check out these graphs. So if you're acquainted with using TensorFlow, or when you explore the using TensorFlow, you can check out something known as a tensor board. So when you create a neural network with TensorFlow, and then if you go to tensor board, you can check out the entire computational graph of the whole neural network. And libraries like TensorFlow actually use this
Again, the problem. So you're not audible.
hello.
Yeah.
Is my screen visible?
Yeah.
Okay. Yeah, so now that we found the gradients, what we do is we can just put the gradients into the gradient descent formula, and then we just run it for a few iterations, and the algorithm will converge to the minimum. So that's all, guys. Any questions you can ask me?
Basically, we don't always have to implement these entire maths, right? Like the
No,
libraries help us a lot.
no. The libraries have all these provisions for that.
All right.
Yeah.
In Keras is another platform where you can put ML models. There are predefined one line, and you can add one layer to the neural network. I mean, you don't have to implement the math.
Take some questions. If the attendees have any questions, you can put it in the chat box or Q&A section. I think this question was answered already.
The one in the Q&A section, right? I think it's answered. Gradient descent is not clear. Okay. Okay, so I'll just share my screen. Oh, it's already sharing. Okay. Can you see the whiteboard? Hello? Yeah, can you see my screen? Can you see the whiteboard, guys?
It's black actually.
Hello, can you guys see my screen again? And can you see the whiteboard now?
All right, yes.
Okay. Maybe I'll just. Okay. So the idea of gradient descent is like this. So suppose I have some loss function like this. Okay. So I want to calculate. I want to find out. So this is my loss function value, and then here I have the parameters. A parameter basically. So what we need to do is we want to minimize this loss function. So we want to find something like this. We want to find this area here. So what is the procedure for gradient descent is we start somewhere on this thing. Start somewhere here. Also we can start here. Okay. So if we start here, so one thing that I want to tell you is gradient descent is to find some local minima. So it is not a method for finding the global minima. There is no known way to find the global minimas. Okay. So what we do is we start at some point and we find the gradient over here. So it is possible that the gradient over here is actually sloping upwards like this. And gradient gives you the direction of the maximum steepness, right? So once we find the gradient, we know that if something is in the direction of maximum steepness, the opposite way will be the where I will be the direction which I have to go to descend maximum. So what we do is we go in the opposite direction for one step to some direction over here. We reach here, and then we calculate this thing again. So we come down here again, and then this happens. So if we come down here now, probably when we calculate the gradient tells me a direction like this, and I end up somewhere over here. So now the gradient will tell me to go like this. So I end up coming somewhere here. So this.
You're not audible.
Hello.
Go ahead.
Yeah. So was my explanation of gradient descent clear? Like right now. Hello. Tanjib Ahmed Siddiqui. Okay. So Siddharthini Nayak is asking, by parameters, do we mean the weights or the input variables? By parameters, you mean the weights, not the input variables. We don't want to differentiate with respect to the input variables because input variables are not changeable. It's by definition it's a data that you observe, so you can't tune the input variables. So we only find the parameters themselves are the weights and the biases in the model. Hope that answers your question.
Any more questions? Manish and Poornima, maybe you can tell us what are the next steps. For example, of course, we have from the Programming Society, we have published a roadmap long time back. I think that's a good thing. But other than that, if you have any special suggestions that the attendees can try, so that would be good.
Uh, I mean, like machine learning is actually quite an interdisciplinary field actually. So I mean, like roadmaps actually kind of help sometimes, but sometimes you have to use your own curiosity to explore. That's something which I find very useful. Hello. But then yeah, like you need to be ready to face some math, and like if you want proper understanding of how these things work, uh, you'll have to be ready to face some math.
Yeah, if you want to explore, you can check out these online courses also. I mean, it's like really good for gaining a fundamental understanding. Like you can check out the Andrew NG courses on Coursera. So those are like the basic courses like you can do to gain a good grip on it. And but of course, it's all about like exploring and like searching new things and reading about them. It just like depends on your interest again.
But when it comes to applying machine learning in outside of uh, in some real life application, suppose you want to integrate it with web or something like that, most likely theoretical understanding won't help you. You just have to. It's most likely you'll end up using some pre-trained models, or you'll end up training some models based on trial and error. So it won't. So that is the thing here. So if you are interested in making web as your or web or any other field as your primary thing, and you want to apply ML in that, then my advice is like not to delve into the theoretical parts of ML because it
Yeah,
won't be useful to you.
yeah. When you want to basically create like an application sort of thing, there are many predefined like the models and stuff which you can like check out, and then of course there are APIs and stuff which you can use for use directly also. uh, but again, if you want to go into research or if you want to go in that field, then you'll have to dive into the math. Otherwise, having a basic understanding of how things work and knowing how to like you can just explore how different things are there and you can use it. Like there are things like keras you can try out, TensorFlow keras, and there is this thing called collabs, like where you can it's Google collabs. So it's basically like this online platform to just code, and then you can just check out stuff there and like explore basically. Yeah.
Neural networks is actually a very recent topic. Though neural networks has been there for a very long time, it came into light because in the last 5 years only. So it's not that new of a topic. There are many other machine learning methods which can be used also. For regular data and all, you can use simple machine learning methods. You don't have to use neural networks, but neural networks are mostly used for
Manish, you're not audible.
hello. Yeah, so neural networks are mainly used for not used for simple machine learning stuff. It's mostly used for complicated stuff like image processing or uh, language recognition, speech recognition, these kind of stuff. Any other questions anyone has? Yes, I'll do that. 1 minute. Siddharthani Nayak, can you again explain the last slide of backpropagation, where the loss function was mapped back to the weights? Yes, 1 minute. Is my screen visible?
Yeah.
Okay, so the idea is we want to calculate gradients of the loss function with respect to the weights and biases. So the weights and biases are the parameters here. Okay, let's be clear on that. So we want to find out the derivative of loss function with respect to the bias, for example. So what does the idea, what does this tell me? How to find out the gradient tell me? I basically list out, if I want to find out the gradient of f with respect to t, I list out all the paths that go from f to t, and then I add the gradients along each of the paths. So that is what we do here. So the idea is, if I want to find out the paths that go from this loss function to b, there's only one path that does so. So I just multiply the gradients along this path, and that gives me the gradient of loss function with respect to bias. Similarly, I can find out the gradient of loss function with respect to the to W0 and W1, and there's only one path that does so. I just have to go like this and come here. I just have to go like this and I have to come here. So if I just multiply all the gradients along this path, and then I will get the weights, and then I will get the gradient of the loss function with respect to the weights. So once I have all the gradients, I have the gradient of loss function with respect to bias and with respect to W0 and with respect to W1. So now I just have to do this gradient descent. So the gradient descent, so I have the gradients basically. So if I just remove this part here. So I suppose I am here currently I am in this position. My parameters are having this value here like this. I want to somehow reach here. So I have found out the values of gradients here. So I know in which direction to move now. Actually, this is more intuitive since it's a two-dimensional thing that I've drawn here. There are only two directions possible. But if I have, suppose if the surface is coming out of the screen also for you guys, so then there'll be a lot of directions in which I can move. So the gradient gives me the direction in which I can move. And then the moment I know the direction in which I can move, I can just take a step in that direction of some particular size, fixed size. And then we can repeat the procedure again. So that is the idea behind so backpropagation is used to calculate this direction, and then gradient descent tells me how to use the direction to move towards the minimum. I hope I'm clear with that. Any more questions? So how many of you are interested in pursuing ML? You guys can you can tell in the chat box. Okay, nice. So you can, as Poornima suggested, you can take up some courses on Coursera also. Like it's like some of the courses are really good, especially the first one, the Andrew Ng's Introduction to Machine Learning one, that gives you a brief overview of every.
Another suggestion is, if you are interested, do stay in touch with people who are already doing ML, like Manish, Poornima, and there are many other people who would be subsequently taking up some sessions. And other than these people also, if you know anyone who are into ML or doing some projects, stay in touch and get to know how they do things.
Yeah, I think we would be having another session, like others who are into ML would be taking another session, which would include coding also. So like something like a hands-on experience. So do try to attend that also. That would like basically help you to see how do you actually code whatever you learned today, or similar things.
So I guess we can stop the session now, and we will be mailing you all the links, and maybe the slides. We will be mailing you soon. Manish, if you have anything to add.
Yeah, just one point. Like in case you are looking for some sort of reasons for learning, some theoretical reasons for some particular concept in ML. Like many of these things are actually many of these the reasons are actually from probability side. So if you have done some, if probably in in your second year, either in the third or fourth semester, you'll be having some courses on probability. So once you're done with those courses, it'll help you a lot in understanding the theoretical reasons behind these concepts. That's all I have to say.
All right. Thank you, Manish and Poornima. The session was great. And I will request the attendees to attend tomorrow's session as well. We have a session on object oriented programming. It is a very important topic from the placements perspective as well. And even when you go into the industry for your professional work, most of the industries follow this paradigm of programming, and so getting exposed to this topic will help you a lot later. So I hope you will join the session tomorrow as well, and also the machine learning session that will be dealing hands-on machine learning, that would be delivered by Shravya and Srikant probably. So of course we will inform you when the session is, and I hope that you will attend that too. So thank you, Manish and Poornima. I guess we can stop.
Yeah, thanks a lot, Ashay. Hope you guys enjoyed it. At least learned like the basic of what we wanted to say. Yeah.
Basically, like I hope like this session has given you some markers to start exploring. So you have some markers and you can start exploring from those perspectives. I hope it has been useful in that sense at least. You may not have got a hand of everything that we told you guys, but at least if you certain terms, if you had understood, if you had caught those terms, it'll be really useful if you Google search them and you can explore on.
Okay. Thank you so much. Thank you so much for attending.
Thank you guys, and thank you, Ashay.
Yeah, thanks everyone.